हेलो एवरीवन। आज हम क्लास 12 केमिस्ट्री एनसीईआरटी की बुक से यूनिट 6 जनरल प्रिंसिपल्स एंड प्रोसेसेस ऑफ आइसोलेशन ऑफ एलिमेंट्स का रीडिंग करेंगे। ये एक ऑडियो बुक है रिवीजन पर्पस के लिए, इसमें किसी भी टाइप का एक्सप्लेनेशन नहीं है। Thermodynamics illustrates why only a certain reducing element and a minimum specific temperature are suitable for reduction of a metal oxide to the metal in an extraction. The history of civilization is linked to the use of metals in antiquity in many ways. Different periods of early human civilizations have been named after metals. The skill of extraction of metals gave many metals and brought about several changes in the human society. It gave weapons, tools, ornaments, utensils, etc., and enriched the cultural life. The seven metals of antiquity, as they are sometimes called, are gold, copper, silver, lead, tin, iron, and mercury. Although modern metallurgy had exponential growth after Industrial Revolution, it is interesting to note that many modern concepts in metallurgy have their roots in ancient practices that predated the Industrial Revolution. For over 7,000 years, India has had a rich tradition of metallurgical skills. The two important sources for the history of Indian metallurgy are archaeological excavations and literary evidences. The first evidence of metal in Indian subcontinent comes from Mehergarh in Balochistan, where a small copper bead dated to about 6000 before the Common Era was found. It is, however, thought to be native copper which has not been extracted from the ore. Spectrometric studies on copper ore samples obtained from the ancient mine pits at Khetri in Rajasthan and on metal samples cut from representative Harappan artifacts recovered from Mitathal in Haryana and 8 other sites distributed in Rajasthan, Gujarat, Madhya Pradesh and Maharashtra prove that copper metallurgy in India dates back to the Chalcolithic cultures in the subcontinent. Indian Chalcolithic copper objects were in all probability made indigenously. The ore for extraction of metal for making the objects was obtained from chalcopyrite ore deposits in Aravalli Hills. Collection of archaeological texts from copper plates and rock inscriptions have been compiled and published by the Archaeological Survey of India during the past century. Royal records were engraved on copper plates in Briquette Tamrapatra. Earliest known copper plates has a Mauryan record that mentions famine relief efforts. It is one of the very few pre-Ashoka Brahmi inscriptions in India. Harappans also used gold and silver as well as the joint alloy electrum. Variety of ornaments such as pendants, bangles, beads and rings have been found in ceramic or bronze pots. Early gold and silver ornaments have been found from Indus Valley sites such as Mohenjo-daro in Briquette 3000 before the Common Era. These are on display in the National Museum, New Delhi. India has the distinction of having the deepest ancient gold mines in the world in the Maski region of Karnataka. Carbon dating places them in mid-1st millennium before the Common Era. Hymns of Rigveda gave earliest indirect references to the alluvial placer gold deposits in India. The river Sindhu was an important source of gold in ancient times. It is interesting that the availability of alluvial placer gold in the river Sindhu has been reported in modern times also. It has been reported that there are great mines of gold in the region of Mansarovar and Thokjalyu even now. The Pali text Anguttara Nikaya narrates the process of the recovery of gold dust or particles from the alluvial placer gold deposits. Although evidence of gold refining is available in Vedic texts, it is Kautilya's Arthashastra, authored probably in 3rd or 4th century before the Common Era during Mauryan era, which has much data on prevailing chemical practices in a long section on mines and minerals, including metal ores of gold, silver, copper, lead, tin, and iron. Kautilya describes a variety of coal, ras vidya, which is naturally occurring gold solution. Kalidas also mentioned about such solutions. It is astonishing how people recognize such solutions. The native gold has different colors depending upon the nature and amount of impurity present in it. It is likely that the different colors of native gold were a major driving force for the development of gold refining. Recent excavations in central parts of Ganges Valley and Vindhya Hills have shown that iron was produced there possibly as early as in 1800 before the Common Era. In the recent excavations conducted by the Uttar Pradesh State Archaeological Department, iron furnaces, artifacts, tuyeres, and layers of slag have been found. Radiocarbon dating places them between before the Common Era 1800 and 1000. The results of excavation indicate that the knowledge of iron smelting and manufacturing of iron artifacts was well known in eastern Vindhyas, and it was in use in the central Ganga plains at least from the early 2nd millennium before the Common Era. The quantity and types of iron artifacts and the level of technical advancements indicate that working of iron would have been introduced much earlier. The evidence indicates early use of iron in other areas of the country, which proves that India was indeed an independent center for the development of the working of iron. Iron smelting and the use of iron was specially established in South Indian megalithic cultures. The forging of wrought irons seems to have been at peak in India in the 1st millennium Common Era. Greek accounts report the manufacture of steel in India by crucible process. In this process, iron, charcoal and glass were mixed together in a crucible and heated until the iron melted and absorbed the carbon. India was a major innovator in the production of advanced quality steel. Indian steel was called the wonder material of the Orient. A Roman historian, Quintus Curtius, records that one of the gifts Porus of Taxila in Briquette 326 before the Common Era gave to Alexander the Great was some 2.5 tons of wood steel. Wood steel is primarily iron containing a high proportion of carbon, in Briquette 1.0 to 1.9%. Woods is the English version of the word uku, which is used for steel in Karnataka and Andhra Pradesh. Literary accounts suggest that Indian wood steel from southern part of the Indian subcontinent was exported to Europe, China and Arab world. It became prominent in the Middle East, where it was named as Damascus steel. Michael Faraday tried to duplicate this steel by alloying iron with a variety of metals, including noble metals, but failed. When iron ore is reduced in solid state by using charcoal, porous iron blocks are formed. Therefore, reduced iron blocks are also called sponge iron blocks. Any useful product can be obtained from this material only after removing the porosity by hot forging. The iron so obtained is termed as wrought iron. An exciting example of wrought iron produced in ancient India is the world-famous iron pillar. It was erected in its present position in Delhi in 5th century Common Era. The Sanskrit inscription engraved on it suggests that it was brought here from elsewhere during the Gupta period. The average composition in bracket weight in percentage of the components present in the wrought iron of the pillar besides iron are 0.15% carbon, 0.05% silicon, 0.05% manganese, 0.25% phosphorus, 0.005% nickel, 0.03% copper and 0.02% nitrogen. The most significant aspect of the pillar is that there is no sign of corrosion in spite of the fact that it has been exposed to the atmosphere for about 1600 years. Radiocarbon dating of charcoal from iron slag revealed evidence of continuous smelting in Khasi Hills of Meghalaya. The slag layer, which is dated to 353 before the Common Era to Common Era 128, indicates that Khasi Hill region is the earliest iron smelting site studied in the entire region of northeast India. The remnants of former iron ore excavation and iron manufacturing are visible even now in the landscape of Khasi Hills. British naturalists who visited Meghalaya in early 19th century described the iron industry that had developed in the upper part of the Khasi Hills. There is archaeological evidence of zinc production in Rajasthan mines at Zawar from the 6th or 5th before the Common Era. India was the first country to master zinc distillation. Due to low boiling point, zinc tends to vaporize while its ore is smelted. Pure zinc could be produced after a sophisticated downward distillation technique in which the vapor was condensed in a lower container. This technique was also applied to mercury. Indian metallurgists were masters in this technique. This has been described in Sanskrit text of 14th century. Indians had knowledge about mercury. They used it for medicinal purpose. Development of mining and metallurgy declined during the British colonial era. By the 19th century, once flourished mines of Rajasthan were mostly abandoned and became almost extinct. In 1947, when India got independence, European literature on science had already found its way slowly into the country. Thus, in post-independence era, the government of India initiated the process of nation building through the establishment of various institutes of science and technology. In the following sections, we will learn about the modern methods of extraction of elements. 6.1 Occurrence of Metals. A few elements like carbon, sulfur, gold and noble gases occur in free state, while others are found in combined forms in the Earth's crust. Elements vary in abundance. Among metals, aluminium is the most abundant. In fact, it is the third most abundant element in Earth's crust. In bracket 8.3% approximate by weight. It is a major component of many igneous minerals including mica and clays. Many gemstones are impure forms of Al2O3. For example, gems ruby and sapphire have chromium and cobalt respectively as impurity. Iron is the second most abundant metal in the Earth's crust. It forms a variety of compounds and the various uses make it a very important element. It is one of the essential elements in biological systems as well. For obtaining a particular metal, first we look for minerals which are naturally occurring chemical substances in the Earth's crust and are obtained through mining. Out of many minerals in which a metal may be found, only a few are viable to be used as source of that metal. Such minerals are known as ores. The principal ores of aluminium, iron, copper and zinc are given in Table 6.1. Table 6.1 Principal ores of some important metals. A particular element may occur in a variety of compounds. The process of isolation of element from its compound should be such that it is chemically feasible and commercially viable. For the purpose of extraction, bauxite is chosen for aluminium. For iron, usually the oxide ores which are abundant and do not produce polluting gases in briquette like sulfur dioxide that is produced in case of iron pyrites are taken. For copper and zinc, any of the ores listed in Table 6.1 may be used depending upon the availability and other relevant factors. The entire scientific and technological process used for isolation of the metal from its ore is known as metallurgy. The extraction and isolation of an element from its combined form involves various principles of chemistry. Still, some general principles are common to all the extraction process of metals. An ore rarely contains only a desired substance. It is usually contaminated with earthly or undesired materials known as gangue. The extraction and isolation of metals from ores involves the following major steps: concentration of the ore, isolation of the metal from its concentrated ore, and purification of the metal. In the following sections, we shall first describe the various steps for effective concentration of ores. After that, principles of some of the common metallurgical processes will be discussed. Those principles will include the thermodynamic and electrochemical aspects involved in the effective reduction of the concentrated ore to the metal. 6.2 Concentration of ores. Removal of the unwanted materials in bracket, for example sand, clays, etc. from the ore is known as concentration, dressing or benefaction. Before proceeding for concentration, ores are graded and crushed to reasonable size. Concentration of ores involves several steps and selection of these steps depends upon the differences in physical properties of the compound of the metal present and that of the gangue. The type of the metal, the available facilities and the environmental factors are also taken into consideration. Some of the important procedures for concentration of ore are described below. 6.2.1 Hydraulic washing. This is based on the difference between specific gravities of the ore and the gangue particles. It is therefore a type of gravity separation. In one such process, an upward stream of running water is used to wash the powdered ore. The lighter gangue particles are washed away and the heavier ore particles are left behind. 6.2.2 Magnetic separation. This is based on differences in magnetic properties of the ore components. If either the ore or the gangue is attracted towards magnetic field, then the separation is carried out by this method. For example, iron ores are attracted towards magnet, hence non-magnetic impurities can be separated from the using magnetic separation. The powdered ore is dropped over a conveyor belt which moves over a magnetic roller. In bracket figure 6.1, magnetic substance remains attracted towards the belt and falls close to it. (6.2.3) Froth flotation method. This method is used for removing gangue from sulfide ores. In this process, a suspension of the powdered ore is made with water. Collectors and froth stabilizers are added to it. Collectors in bracket, for example, pine oils, fatty acids, xanthates, etc. enhance non-wettability of the material particles, and froth stabilizers. In Briquette, for example, creosotes, aniline stabilize the froth. The mineral particles become wet by oils while the gangue particles by water. A rotating pedal agitates the mixture and draws air in it. As a result, froth is formed which carries the mineral particles. The froth is light and is skimmed off. It is then dried for recovery of the ore particles. Sometimes it is possible to separate two sulfide ores by adjusting proportion of oil to water or by using depressants. For example, in the case of an ore containing zinc sulfide and lead sulfide, the depressant used is sodium cyanide. It selectively prevents zinc sulfide from coming to the froth but allows lead sulfide to come with the froth. The innovative washerwoman. One can do wonders if he or she has a scientific temperament and is attentive to observations. A washerwoman had an innovative mind too. While washing a miner's overalls, she noticed that sand and similar dirt fell to the bottom of the washtub. What was peculiar, the copper-bearing compounds that had come to the clothes from the mines were caught in the soap suds and so they come to the top. One of her clients, Mrs. Carrie Everson, was a chemist. The washerwoman told her experience to Mrs. Everson. The latter thought that idea could be used for separating copper compounds from rocky and earth materials on large scale. This way, an invention came up. At that time, only those ores were used for extraction of copper which contained large amounts of the metal. Invention of the froth flotation method made copper mining profitable even from the low-grade ores. World production of copper soared and the metal became cheaper. 6.2.4 Leeching. Leeching is often used if the ore is soluble in some suitable solvent. Following examples illustrate the procedure. A. Leeching of alumina from bauxite. Bauxite is the principal ore of aluminium. It usually contains silicon dioxide, iron oxide, and titanium oxide as impurities. Concentration is carried out by heating the powdered ore with a concentrated solution of sodium hydroxide at 473 to 523 Kelvin and 35 to 36 bar pressure. This process is called digestion. This way, aluminum oxide is extracted out as sodium aluminate. The impurity silicon dioxide too dissolves, forming sodium silicate. Other impurities are left behind. Aluminium oxide plus sodium hydroxide plus H2O give you sodium tetrahydroxyaluminate. I am reading this reaction again. Al2O3 in solid phase plus 2NaOH in aqueous phase plus 3H2O in liquid phase gives 2Na in square bracket AlOH4, that is in aqueous phase. The sodium aluminate present in solution is neutralized by passing carbon dioxide gas and hydrated Al2O3 is precipitated. At this stage, small amount of freshly prepared sample of hydrated Al2O3 is added to the solution. This is called seeding. It induces the precipitation. Sodium tetrahydroxyaluminate in aqueous phase plus 2 carbon dioxide in gaseous phase gives Al2O3 into XH2O in solid phase plus 2NaHCO3 in aqueous phase. Sodium silicate remains in the solution and hydrated alumina is filtered, dried and heated to give back pure Al2O3. Al2O3 into XH2O in solid phase in presence of 1470 Kelvin temperature gives Al2O3 in solid phase plus XH2O in gas phase. B. Other examples. In the metallurgy of silver and gold, the respective metal is leached with a dilute solution of NaCN or KCN in the presence of air which supplies O2. The metal is obtained later by replacement reaction. 4 metal in solid phase plus 8 Cn minus ion in aqueous phase plus 2 H2O in aqueous phase plus O2 in gaseous phase gives 4 in square bracket metal in small bracket Cn twice minus ion in aqueous phase plus 4 OH minus ion in aqueous phase. In bracket metal is equals to silver or gold. 2 MCN2 minus iron in aqueous phase plus zinc in solid phase gives tetracyanozincate ion in aqueous phase plus 2 metal in solid phase. 6.3 Extraction of crude metal from concentrated ore. To extract metal from concentrated ore, it must be converted to a form which is suitable for reduction to metal. Usually sulfide ores are converted to oxide before reduction because oxides are easier to reduce. Thus, isolation of metals from concentrated ore involves two major steps, namely conversion to oxide and reduction of the oxide to metal. A. Conversion to oxide. First, calcination. Calcination involves heating. It removes the volatile matter which escapes, leaving behind the metal oxide. Fe2O3 into XH2O in solid phase in presence of heat gives Fe2O3 in solid phase plus XH2O in gas. ZnCO3 in solid phase in presence of heat gives ZnO in solid phase plus CO2 in gas phase. CaCO3 into MgCO3 in solid phase in presence of heat gives CaO in solid phase plus MgO in solid phase plus 2CO2 in gas. Second, roasting. In roasting, the ore is heated in a regular supply of air in a furnace at a temperature below the melting point of the metal. Some of the reactions involving sulfide ores are 2ZnS plus 3O2 gives 2ZnO plus 2SO2. 2PbS plus 3O2 gives 2PbO plus 2SO2. 2CO2S plus 3O2 gives 2CO2O plus 2SO2. The sulfide ores of copper are heated in reverberatory furnace in bracket figure 6.3. If the ore contains iron, it is mixed with silica before heating. Iron oxide slags off as iron silicate and copper is produced in the form of copper matte which contains Cu2S and FeS. FeO plus SiO2 gives FeSiO3 in bracket slag. The SO2 produced is utilized for manufacturing H2SO4. B. Reduction of oxide to the metal. Reduction of the metal oxide usually involves heating it with a reducing agent, for example carbon or carbon monoxide or even another metal. The reducing agent, for example carbon, combines with the oxygen of the metal oxide. MXOY plus Y carbon gives XM plus Y carbon monoxide. Some metal oxides get reduced easily while others are very difficult to be reduced. In bracket, reduction means electron gain by the metal ion. In any case, heating is required. 6.4 Thermodynamic Principles of Metallurgy. Some basic concepts of thermodynamics help us in understanding the theory of metallurgical transformations. Gibbs energy is the most significant term. To understand the variation in the temperature required for the thermal reductions and to predict which element will suit as the reducing agent for a given metal oxide, in bracket MXOY, Gibbs energy interpretations are made. The criterion for the feasibility of a thermal reduction is that at a given temperature, Gibbs energy change of the reaction must be negative. The change in Gibbs energy, delta G, for any process at any specified temperature is described by the equation delt G is equals to delt H minus T delt S, where delt H is the enthalpy change and delt S is the entropy change for the process. When the value of delt G is negative in equation 6.14, only then the reaction will proceed. Delt G can become negative in the following situations. First, if delt S is positive on increasing the temperature T, the value of T delt S increases so that delt H is less than the T delt S. In this situation, delt G will become negative on increasing temperature. Second, if coupling of the two reactions, that is reduction and oxidation, results in negative value of delt G for overall reaction, the final reaction becomes feasible. Such coupling is easily understood through Gibbs energy. In bracket, delta R G0 versus T plots for the formation of oxide. In bracket figure 6.4. These plots are drawn for free energy changes that occur when the 1 gram mole of oxygen is consumed. The graphical representation of Gibbs energy was first used by H.J.T. Ellingham. This provides a sound basis for considering the choice of reducing agent in the reduction of oxides. This is known as Ellingham Diagram. Such diagrams help us in predicting the feasibility of thermal reduction of an ore. As we know, during reduction, the oxide of a metal decomposes and the reducing agent takes away the oxygen. The role of reducing agent is to provide delta R G0 negative and large enough to make the sum of delta R G0 of the two reactions, that is oxidation of the reducing agent and reduction of the metal oxide negative. MXO in solid state gives XM in bracket solid or liquid plus 1/2 O2 in gas state. In bracket delta R G0 in small bracket MXO comma capital M. If reduction is carried out by carbon, the oxidation of the reducing agent in bracket, that is carbon, will be there. Carbon in solid phase plus 1/2 O2 in gas phase gives carbon monoxide in gas phase. There may also be complete oxidation of carbon to carbon dioxide. 1/2 carbon in solid phase plus 1/2 O2 in gas phase gives 1/2 carbon dioxide in gas phase. On coupling in bracket combining or combing reaction 6.15 and 6.16, we get MXO in solid phase plus carbon in solid phase gives XM in solid or liquid plus carbon monoxide in gas phase. On coupling reaction 6.15 and 6.17, we have MXO in solid phase plus 1/2 carbon in solid phase gives XM in solid or liquid phase plus 1/2 carbon dioxide in gas phase. Similarly, if carbon monoxide is reducing agent, reaction 6.15 and 6.20 given below need to be coupled. Carbon monoxide in gas phase plus 1/2 oxygen molecule in gas phase gives carbon dioxide in gas phase. Overall reaction will be as follows. MXO in solid phase plus carbon monoxide in gas phase gives XM in solid or liquid phase plus carbon dioxide in gas phase. Ellingham diagram. A. Ellingham diagram normally consists of plots of delta F G naught versus T for the formation of oxides of common metals and reducing agents, that is for the reaction given below. 2xm in solid phase plus O2 in gaseous phase gives 2mxO in solid phase. In this reaction, gas is consumed in the formation of oxide, hence molecular randomness decreases in the formation of oxide, which leads to a negative value of delta S. As a result, sign of T delta S term in equation 6.14 becomes positive. Subsequently, delta F G naught shift toward higher side despite rising T. The result is positive slope in the curve for most of the reactions for the formation of MXO in solid phase. B. Each plot is a straight line and slopes upward except when some change in phase in briquette, solid to liquid or liquid to gas takes place. The temperature at which such change occurs is indicated by an increase in the slope on positive side. In briquette, for example, in the zinc oxide plot, the melting is indicated by an abrupt change in the curve. In briquette, figure 6.4. C. When temperature is raised, a point is reached in the curve where it crosses delta Rg naught is equals to 0 line. Below this temperature, delta Rg naught for the formation of oxide is negative, so MXO is stable. Above the point, free energy of formation of oxide is positive. The oxide MXO will decompose on its own. D. Similar diagrams are constructed for sulfides and halides also. From them, it becomes clear that why reduction of MXS is difficult. Limitations of Ellingham diagram. First, the graph simply indicates whether a reaction is possible or not. That is, the tendency of reduction with a reducing agent is indicated. This is so because it is based only on the thermodynamic concept. It does not explain the kinetics of the reduction process. It cannot answer questions like how fast reduction can proceed. However, it explains why the reactions are sluggish when every species is in solid state and smooth when the ore melts down. It is interesting to note here that delta H in briquette enthalpy change and delta S in briquette entropy change values for any chemical reaction remain nearly constant even on varying temperature. So the only dominant variable in equation 6.14 becomes temperature. However, delta S depends much on the physical state of the compound. Since entropy depends on disorder or randomness in the system, it will increase if a compound melts. In briquette, solid to liquid or vaporizes. In briquette, liquid to gas, since molecular randomness increases on changing the phase from solid to liquid or from liquid to gas. Second, the interpretation of delta Rg naught is based on K. In briquette, delta G naught is equals to minus RT ln K. Thus, it is presumed that the reactants and products are in equilibrium. MXO plus A reduction gives XM plus A reduction O. This is not always true because the reactant or product may be solid. In commercial processes, reactants and products are in contact for a short time. The reactions 6.18 and 6.21 describe the actual reduction of the metal oxide MXO that we want to accomplish. The delta R G naught values for these reactions in general can be obtained from the corresponding delta F G naught values of oxides. As we have seen, heating in briquette, that is increasing temperature, favors a negative value of delta R G naught. Therefore, the temperature is chosen such that the sum of delta Rg naught in the two combined redox process is negative. In delta Rg naught versus T plots, in briquette Ellingham diagram, figure 6.4, this is indicated by the point of intersection of two curves, that is, the curve for the formation of MXO and that for the formation of the oxide of the reducing substance. After that point, the delta R G0 value becomes more negative for the combined process, making the reduction of MXO possible. The difference in the two delta R G0 values after that point determines whether reduction of the oxide of the element of the upper line is feasible by the element of which oxide formation is represented by the lower line. If the difference is large, the reduction is easier. Example 6.1 suggests a condition under which magnesium could reduce alumina. Solution: the two equations are A. 4 by 3 aluminium plus O2 gives 2 by 3 Al2O3. B. 2 magnesium plus O2 gives 2 MgO. At the point of intersection of the Al2O3 and MgO curves, in Briquette marked A in diagram 6.4, the delta R G0 becomes 0 for the reaction. 2 by 3 Al2O3 plus 2 Mg gives 2 MgO plus 4 by 3 aluminium. Below that point, magnesium can reduce alumina. Example 6.2. Although thermodynamically feasible, in practice, magnesium metal is not used for the reduction of alumina in the metallurgy of aluminium. Why? Solution: temperatures below the point of intersection of Al2O3 and MgO curves, magnesium can reduce alumina, but the process will be uneconomical. Example 6.3. Why is the reduction of a metal oxide easier if the metal formed is in liquid state at the temperature of reduction? Solution: the entropy is higher if the metal is in liquid state than when it is in solid state. The value of entropy change in Briquette delta S of the reduction process is more on positive side when the metal formed is in liquid state and the metal oxide being reduced is in solid state. Thus, the value of delta R G0 becomes more on negative side and the reduction becomes easier. 6.4.1 Applications. A. Extraction of iron from its oxides. After concentration, mixture of oxide ores of iron in Briquette Fe2O3, Fe3O4 is subjected to calcination or roasting to remove water, to decompose carbonates and to oxidize sulfides. After that, these are mixed with limestone and coke and fed into a blast furnace from its top, in which the oxide is reduced to the metal. In the blast furnace, in Briquette figure 6.5, reduction of iron oxide takes place at different temperature ranges. A blast of hot air is blown from the bottom of the furnace by burning coke in the lower portion to give temperature up to about 2200 Kelvin. The burning of coke therefore supplies most of the heat required in the process. The carbon monoxide and heat move to the upper part of the furnace. In upper part, the temperature is lower and the iron oxide in Briquette Fe2O3 and Fe3O4 coming from the top are reduced in steps to FeO. These reactions can be summarized as follows. At 500 to 800 Kelvin in Briquette lower temperature range in the blast furnace, Fe2O3 is first reduced to Fe3O4 and then to FeO. 3 Fe2O3 plus carbon monoxide gives 2 Fe3O4 plus carbon dioxide. Fe3O4 plus 4 carbon monoxide gives 3 Fe plus 4 carbon dioxide. Fe2O3 plus carbon monoxide gives 2 FeO plus carbon dioxide. Limestone is also decomposed to calcium oxide, which removes silicate impurity of the ore as slag. The slag is in molten state and separates out from iron. At 900 to 1500 Kelvin in Briquette higher temperature range in the blast furnace, carbon plus carbon dioxide gives 2 carbon monoxide. FeO plus carbon monoxide gives Fe plus CO2. Thermodynamics helps us to understand how coke reduces the oxide and why this furnace is chosen. One of the main reduction steps in this process involves reaction 6.27 given below. FeO in solid phase plus carbon in solid phase gives Fe in solid or liquid phase plus carbon monoxide in gaseous phase. This reaction can be seen as a reaction in which two simpler reactions have coupled. In one, the reduction of FeO is taking place, and in the other, carbon is being oxidized to carbon monoxide. FeO in solid phase give Fe in solid phase plus 1/2 O2 in gas phase. Carbon in solid phase plus 1/2 O2 in gas phase gives carbon monoxide in gas phase. When both the reactions take place to yield the equation 6.27, the net Gibbs energy change becomes delta Rg naught for carbon or carbon monoxide plus delta Rg naught for Fe or Fe is equals to delta Rg naught. Naturally, the resultant reaction will take place when the right hand side in equation 6.30 is negative. In delta Rg naught versus temperature plot representing the change, Fe to FeO in figure 6.6 goes upward, and that representing the change carbon to carbon monoxide in bracket carbon comma carbon monoxide goes downward. They cross each other at about 1073 Kelvin. At temperatures above 1073 Kelvin, approximate the carbon, carbon dioxide line is below the Fe, FeO line. So, above 1073 Kelvin in the range of temperature 900 to 1500 Kelvin, coke will reduce iron oxide and will itself be oxidized to carbon monoxide. Let us try to understand this through figure 6.6. In bracket, approximate values of delta Rg naught are given. At about 1673 Kelvin in bracket 1400 degrees Celsius, delta Rg naught value for the reaction 2FeO gives 2Fe plus O2 is plus 341 kJ per mole. Because it is reverse of Fe gives FeO change, and for the reaction 2 carbon plus O2 gives 2 carbon monoxide, delta Rg naught is minus 447 kJ per mole. If we calculate delta Rg naught value for overall reaction in bracket 6.27, the value will be minus 53 kJ per mole. Therefore, reaction 6.27 become feasible. In a similar way, the reduction of Fe3O4 and Fe2O3 by carbon monoxide at relatively lower temperature can be explained on the basis of lower lying points of intersection of the curves with the carbon monoxide, carbon dioxide curve. The iron obtained from blast furnace contains about 4% carbon and many impurities in smaller amount. In bracket, for example, sulfur, phosphorus, silicon, manganese. This is known as pig iron. It can be molded into variety of shapes. Cast iron is different from pig iron and is made by melting pig iron with scrap iron and coke using hot air blast. It is slightly lower carbon content, in bracket about 3%, and is extremely hard and brittle. Further reductions. Wrought iron or malleable iron is the purest form of commercial iron and is prepared from cast iron by oxidizing impurities in a reverberatory furnace lined with hematite. The hematite oxidizes carbon to carbon monoxide. Fe2O3 plus 3 carbon gives 2Fe plus 3 carbon monoxide. Limestone is added as a flux and sulfur, silicon and phosphorus are oxidized and passed into the slag. The metal is removed and freed from the slag by passing through rollers. B. Extraction of copper from cuprous oxide. In bracket, copper 1 oxide. In the graph of delta Rg naught versus temperature for the formation of oxides, in bracket, In the graph of delta R G0 versus temperature for the formation of oxides, in bracket figure 6.4, the Cu2O line is almost at the top. So it is quite easy to reduce oxide ores of copper directly to the metal by heating with coke. The lines in bracket carbon, carbon monoxide and carbon, carbon dioxide are at much lower position in the graph, particularly after 500 to 600 Kelvin. However, many of the ores are sulfides and some may also contain iron. The sulfide ores are roasted or smelted to give oxides. 2Cu2S plus 3O2 gives 2Cu2O plus 2SO2. The oxides can then be easily reduced to metallic copper using coke. Cu2O plus carbon gives 2Cu plus carbon monoxide. In actual process, the ore is heated in a reverberatory furnace after mixing with silica. In the furnace, iron oxide slags of as iron silicate is formed. Copper is produced in the form of copper matte. This contains copper, Cu2S and FeS. FeO plus SiO2 gives FeSiO3, that is slag. Copper matte is then charged into silica-lined converter. Some silica is also added and hot air blast is blown to convert the remaining FeS, FeO and Cu2S or Cu2O to the metallic copper. Following reactions takes place. 2FeS plus 3O2 gives 2FeO plus 2SO2. FeO plus SiO2 gives FeSiO3. 2Cu2S plus 3O2 gives 2Cu2O plus 2SO2. 2Cu2O plus Cu2S give 6Cu plus SO2. The solidified copper obtained has blistered appearance due to the evolution of sulfur dioxide and so it is called blister copper. C. Extraction of zinc from zinc oxide. The reduction of zinc oxide is done using coke. The temperature in this case is higher than that in the case of copper. For the purpose of heating, the oxide is made into briquettes with coke and clay. ZnO plus carbon in presence of coke and 1673 Kelvin temperature gives Zn plus carbon monoxide. The metal is distilled off and collected by rapid chilling. 6.5 Electrochemical Principles of Metallurgy. We have seen how principles of thermodynamics are applied to pyrometallurgy. Similar principles are effective in the reductions of metal ions in solution or molten state. Here they are reduced by electrolysis or by adding some reducing element. In the reduction of a molten metal salt, electrolysis is done. Such methods are based on electrochemical principles which could be understood through the equation. Delta G0 is equals to minus N E0 F. Here N is the number of electrons and E0 is the electrode potential of the redox couple formed in the system. More reactive metals have large negative values of the electrode potential. So the reduction is difficult. If the difference of two E0 values correspond to a positive E0 and consequently negative delta G0 in equation 6.40, then the less reactive metal will come out of the solution and the more reactive metal will go into the solution. For example, Cu plus 2 in aqueous phase plus Fe in solid phase gives Cu in solid phase plus Fe plus 2 in aqueous phase. In simple electrolysis, the N plus ions are discharged at negative electrodes in bracket cathodes and deposited there. Precautions are taken considering the reactivity of the metal produced and suitable materials are used as electrodes. Sometimes a flux is added for making the molten mass more conducting. Aluminium. In the metallurgy of aluminium, purified Al2O3 is mixed with Na3AlF6 or CaF2, which lowers the melting point of the mixture and brings conductivity. The fused matrix is electrolyzed. Steel vessel with lining of carbon act as cathode and graphite anode is used. The overall reaction may be written as 2Al2O3 plus 3 carbon gives 4 aluminium plus 3 carbon dioxide. This process of electrolysis is widely known as Hall-Héroult process. Thus, electrolysis of the molten mass is carried out in an electrolytic cell using carbon electrodes. The oxygen liberated at anode reacts with the carbon of anode, producing carbon monoxide and carbon dioxide. This way, for each kg of aluminium produced, about 0.5 kg of carbon anode is burnt away. The electrolytic reactions are: at cathode, Al plus 3 melt plus 3 electron gives aluminium in liquid phase. At anode, carbon in solid phase plus O minus 2 in melting state gives carbon monoxide in gaseous phase plus 2 electron release. Carbon in solid state plus 2O minus 2 in melting phase gives carbon dioxide in gas phase plus 4 electron will release. Copper from low-grade ores and scraps. Copper is extracted by hydrometallurgy from low-grade ores. It is leached out using acid or bacteria. The solution containing Cu plus 2 is treated with scrap iron or H2. Equation 6.40, 6.46. Cu plus 2 in aqueous phase plus H2 in gas phase gives copper in solid phase plus 2H plus in aqueous phase. Example 6.4. At a site, low-grade copper ores are available and zinc and iron scraps are also available. Which of the two scraps would be more suitable for reducing the leached copper or and why? Solution: zinc being above iron in the electrochemical series, in bracket more reactive metal is zinc. The reduction will be faster in case zinc scraps are used. But zinc is costlier metal than iron, so using iron scraps will be advisable and advantageous. 6.6 Oxidation Reduction. Besides reductions, some extractions are based on oxidation, particularly for nonmetals. A very common example of extraction based on oxidation is the extraction of chlorine from brine. In bracket, chlorine is abundant in seawater as common salt. 2Cl minus in aqueous phase plus 2H2O in liquid phase gives 2OH minus in aqueous phase plus H2 in gaseous phase plus Cl2 in gas phase. The delta G naught for this reaction is plus 422 kilojoule. When it is converted to E naught in bracket using delta G naught is equals to minus E naught F, we get E naught is equals to minus 2.2 volt. Naturally, it will require an external EMF that is greater than 2.2 volt, but the electrolysis requires an excess potential to overcome some other hindering reactions in bracket unit 3 section 3.5.1. The Cl2 is obtained by electrolysis giving out H2 and aqueous NaOH as byproducts. Electrolysis of molten NaCl is also carried out, but in that case sodium metal is produced and not NaOH. As studied earlier, extraction of gold and silver involves leaching the metal with cyanide ion. This is also an oxidation reaction in bracket Ag to Ag plus or Au to Au plus. The metal is later recovered by displacement method. 4Au in solid phase plus 8Cn minus in aqueous phase plus 2H2O in aqueous phase plus O2 in gaseous phase gives 4 in bracket AuCN twice negative ion in aqueous phase plus 4OH minus in aqueous phase. 2 in bracket AuCN twice Negative iron in aqueous phase plus zinc in solid phase gives 2 gold in solid phase plus tetracyanozincate in aqueous phase. In this reaction, zinc acts as a reducing agent. (6.7) Refining. A metal extracted by any method is usually contaminated with some impurity. For obtaining metals of high purity, several techniques are used depending upon the differences in properties of the metal and the impurity. Some of them are listed below. A. Distillation. B. Liquefaction. C. Electrolysis. D. Zone refining. E. Vapor phase refining. And F. Chromatographic methods. These are described in detail here. A. Distillation. This is very useful for low boiling metals like zinc and mercury. The impure metal is evaporated to obtain the pure metal as distillate. B. Liquefaction. In this method, a low melting metal like tin can be made to flow on a sloping surface. In this way, it is separated from higher melting impurities. C. Electrolytic refining. In this method, the impure metal is made to act as anode. A strip of the same metal in pure form is used as cathode. They are put in a suitable electrolytic bath containing soluble salt of the same metal. The more basic metal remains in the solution and the less basic ones go to the anode mud. This process is also explained using the concept of electrode potential, overpotential and Gibbs energy, which you have seen in previous sections. The reactions are: at anode, M gives Mn plus N electron; at cathode, Mn plus N electron gives metal. Copper is refined using an electrolytic method. Anodes are of impure copper and pure copper strips are taken as cathode. The electrolyte is acidified solution of copper sulfate, and the net result of electrolysis is the transfer of copper in pure form from the anode to the cathode. At anode, copper give you Cu plus 2 ion plus 2 electron, and at cathode, Cu plus 2 ion plus 2 electron gives you pure copper. Impurities from the blister copper deposit at anode mud, which contains antimony, selenium, tellurium, silver, gold and platinum. Recovery of these elements may meet the cost of refining. Zinc may also be refined this way. D. Zone refining. This method is based on the principle that the impurities are more soluble in the melt than in the solid state of the metal. A mobile heater surrounding the rod of impure metal is fixed at its one end. In bracket figure 6.8. The molten zone moves along with the heater, which is moved forward. As the heater moves forward, the pure metal crystallizes out of the metal left behind and the impurities pass on into the adjacent new molten zone created by movement of heaters. The process is repeated several times and the heater is moved in the same direction again and again. Impurities get concentrated at one end. This end is cut off. This method is very useful for producing semiconductor and other metal of very high purity. For example, germanium, silicon, boron, gallium and indium. E. Vapor phase refining. In this method, the metal is converted into its volatile compound, which is collected and decomposed to give pure metal. So, the two requirements are: first, the metal should form a volatile compound with an available reagent. Second, the volatile compound should be easily decomposable so that the recovery is easy. Following examples will illustrate this technique. Mond process for refining nickel. In this process, nickel is heated in a stream of carbon monoxide forming a volatile complex named as nickel tetracarbonyl. This complex is decomposed at higher temperature to obtain pure metal. Nickel plus 4 carbon monoxide in presence of 330 to 350 Kelvin temperature gives nickel tetracarbonyl. Now nickel tetracarbonyl in presence of 450 to 470 Kelvin temperature gives nickel plus 4 carbon monoxide. One Arcal method for refining zirconium or titanium. This method is very useful for removing all the oxygen and nitrogen present in the form of impurity in certain metals like zirconium and titanium. The crude metal is heated in an evacuated vessel with iodine. The metal iodide being more covalent volatilizes. Zirconium plus 2I2 gives zirconium tetraiodide. The metal iodide is decomposed on a tungsten filament electrically heated to about 1800 Kelvin. The pure metal deposits on the filament. Zirconium tetraiodide gives zirconium plus 2I2. F. Chromatographic methods. You have learnt about chromatographic technique of purification of substance in class 11 in Briquette unit 12. Column chromatography is very useful purification of the elements which are available in minute quantities, and the impurities are not very different in chemical properties from the element to be purified. 6.8 Uses of aluminium, copper, zinc and iron. Aluminium foils are used as wrappers for food materials. The fine dust of the metal is used in paints and lacquers. Aluminium being highly reactive is also used in the extraction of chromium and manganese from their oxides. Wires of aluminium are used as electricity conductors. Alloys containing aluminium being light are very useful. Copper is used for making wires used in electrical industry and for water and steam pipes. It is also used in several alloys that are rather tougher than the metal itself. For example, brass in briquette with zinc, bronze in briquette with tin, and coinage alloy in briquette with nickel. Zinc is used for galvanizing iron. It is also used in large quantities in batteries. It's constituent of many alloys. For example, brass in briquette, copper 60%, zinc 40%, and German silver in briquette, copper 25 to 30%, zinc 25 to 30%, and nickel 40 to 50%. Zinc dust is used as a reducing agent in the manufacture of dye stuffs, paints, etc. Cast iron, which is the most important form of iron, is used for casting stoves, railway sleepers, gutter pipes, toys, etc. It is used in the manufacture of wrought iron and steel. Wrought iron is used in making anchors, wires, bolts, chains and agricultural implements. Steel finds a number of uses. Alloy steel is obtained when other metals are added to it. Nickel steel is used for making cables, automobiles and aeroplane parts, pendulum, measuring tips. Chrome steel is used for cutting tools and crushing machines, and stainless steel is used for cycles, automobiles, utensils, pens, etc. Summary. Although modern metallurgy had exponential growth after Industrial Revolution, many modern concepts in metallurgy have their roots in ancient practices that predated the Industrial Revolution. For over 7,000 years, India has had high tradition of metallurgical skills. Ancient Indian metallurgists have made major contributions which deserve their place in metallurgical history of the world. In the case of zinc and high carbon steel, ancient India contributed significantly for the development of base for the modern metallurgical advancements which induced metallurgical study leading to Industrial Revolution. Metals are required for a variety of purposes. For this, we need their extraction from the minerals in which they are present and from which their extraction is commercially feasible. These minerals are known as ores. Ores of the metals are associated with many impurities. Removal of these impurities to a certain extent is achieved in concentration steps. The concentrated ore is then treated chemically for obtaining the metal. Usually the metal compounds in briquette, for example oxides, sulfides, are reduced to the metal. The reducing agents used are carbon, carbon monoxide, or even some metals. In this reduction process, the thermodynamic and electrochemical concepts are given due consideration. The metal oxide reacts with a reducing agent. The oxide is reduced to the metal and the reducing agent is oxidized. In the two reactions, the net Gibbs energy change is negative, which becomes more negative on raising the temperature. Conversion of the physical states from solid to liquid or to gas and formation of gaseous states favors decrease in the Gibbs energy for the entire system. This concept is graphically displayed in plots of delta G naught versus temperature in Briquette Ellingham diagram for such oxidation reduction reactions at different temperatures. The concept of electrode potential is useful in the isolation of metals in briquette, for example aluminium, gold, silver, where the sum of the two redox couples is positive so that the Gibbs energy change is negative. The metals obtained by usual methods still contain minor impurities. Getting pure metals requires refining. Refining process depends upon the differences in properties of the metal and the impurities. Extraction of aluminium is usually carried out from its bauxite ore by leaching it with sodium hydroxide. Sodium aluminate thus formed is separated and then neutralized to give back the hydrated oxide, which is then electrolyzed using cryolite as a flux. Extraction of iron is done by reduction of its oxide ore in blast furnace. Copper is extracted by smelting and heating in a reverberatory furnace. Extraction of zinc from zinc oxides is done using coke. Several methods are employed in refining the metal. Metals in general are very widely used and have contributed significantly in the development of a variety of industries. A summary of the occurrence and extraction of some metals is presented in the following table. Metal aluminium. Occurrence: first bauxite Al2O3 into XH2O, second cryolite Na3Al(F6). Common method of extraction: electrolysis of Al2O3 dissolved in molten Na3Al(F6). Remarks: for the extraction, a good source of electricity is required. Second, iron. Occurrence: first hematite Fe2O3, second magnetite Fe3O4. Common method of extraction: reduction of the oxide with carbon monoxide and coke in blast furnace. Remarks: temperature approaching 2170 Kelvin is required. Copper. Occurrence: first copper pyrite CuFeS2, second copper glance Cu2S, third malachite CuCO3 into CuOH twice, fourth cuprite Cu2O. Common method of extraction: roasting of sulfide partially and reduction. Remarks: it is self-reduction in a specially designed converter. The reduction takes place easily. Sulfuric acid leaching is also used in hydrometallurgy for low-grade ores. Then zinc metal. Occurrence: zinc blend or sphalerite ZnS, calamine ZnCO3 and zincite ZnO. Common method of extraction: roasting followed by reduction with coke. Remarks: the metal may be purified by fractional distillation.